Today we're going to start a new unit, and our focus today is to estimate distance traveled when the velocity function is not constant and to estimate the area under a curve using a rectangular method. So on the first page of your new packet, we have a table of data here about time and our velocity. So the question says, how far did the car go? So if we're looking for distance, but we're given velocity, distance is rate times time. So the rate is feet per second. The time is seconds. Seconds divide to 1, and we're left with feet. So if I want to estimate the time, if I want to estimate the distance and I'm given rate and time, we can use a rectangular method to find this multiplication, like a length times width and area. So here is the curve for these data points. You can see 0, 20, 130, 338, and if let's say from the left-hand side, I go up to my graph, if I draw a rectangle for every 1 second, that's a little curvy there, but you get the idea. So I have 1, 2, 3, 4, 5 rectangles where if I multiply the rate, which is the y value, times the time, which in this case is 1 second, I would get the distance. So we're going to go from 0 to 5 seconds, and we're going to start with a left-hand estimate. This first rectangle is a height of 20 times a width of 1, plus the next rectangle is a height of 30, a width of 1, plus the next rectangle is this y value at 2, a width of 1, the next rectangle here at 3, a height of 44, a width of 1, and the last one has a height of 48 and a width of 1. And really what I could have done is done 1 times, because I could factor out the ones, and really it's adding up these left y values. So if I just, hard to draw straight lines with this tablet. There we go. So here's the left-hand side of the data. I can add these up. You can take out your calculator, and that gives us 180 feet. So you can do the same thing on the right. Let me draw new rectangles. So if I go up on the right, I get this rectangle, and now here, this rectangle is higher than the one before, this rectangle, and this rectangle. So you can see the right-hand side of our rate multiplied by time, rate up to here multiplied by time. From the right-hand side, we're just going to use these rightmost numbers when calculating the area of these rectangles. So starting on the right, this is a y value of 50 times a width of 1. The next y value is 48 with a width of 1. The next rectangle goes up to 44, and then 38, and then 30. So in our calculator, if we add all those together, we get 210 feet. So the distance traveled by this car is somewhere between 180 and 210 feet. So we're going to say distance is between 180 and 210 feet. It's a pretty wide span or big span of numbers to have an estimate between. So when these rectangles are 1 unit apart, you can't really say exactly what that distance is. So then let's look at every half a second. We're not going to draw, actually, if you look at the bottom, here's the half rectangles. So you can see a rectangle at a half up to the curve, 1, 1 1/2. And these rectangles being a much smaller width look like they give a better estimate. I've got, or even here, I got less overage compared to these right-hand rectangles. Let's label this. This one's right. This one's left. It's left because the left corner of the rectangle is what's on the curve. These are right because the right corner of the rectangle is what's on the curve. So let's find the left hand and the right hand sums for the half second. And I'm not going to do length times width plus length plus width. I'm going to factor it out. So if I look at our left-hand data, I start on the left, and we're going to include everything except the last data point. Because if we look down here at our rectangles, this left corner is at the height here at 4 1/2. I don't have another height at 5 because that would be past my graph. Okay, so each rectangle is going to have a width of a half, and then we've got 20 plus 26 plus 30 plus 35 plus 38. So I'm going to add all of these y values together times a half. We can type that in our calculator, and that gets us 189 feet. Okay, so let's do the right-hand side. We're going to start on the right and go all the way, not including that very left-hand number. We'll start on the right, leave out this last number there. So that's 1/2 times. You can write your numbers backwards. You can write your numbers forwards. I'm just going to start here at the 26. Type it all in your calculator, and we get 204 feet. So now with half-second intervals of rate, I'm going to estimate that the distance is between 189 feet and 204 feet. So better, not great, but still better. What would be even better is 1/4 of a second, 1/10 of a second. That would be an even better estimate. And that's where we're going in this unit. The calculus is going to be the infinite number of rectangles, not just these every half second. We're going to get to infinite numbers of rectangles later as we keep going. Okay, so let's try this again on the next page. We've got 2 graphs here, and estimate the area bounded by the graph, the x and y axis, and when x is 6. So these grids, they stop at 6, so that's good. We don't have to stop. Use 2 rectangles. So if I need 2 rectangles from 0 to 6, I want to find out, well, how wide will the rectangles be? So I'm going to call that width. And if we're going from an x of 0 to an x of 6, that distance in between is 6 minus 0. I want 2 even rectangles. So every 3 units will cut off our rectangles. So on the left, so left-hand sum, I start on the left at 0. I go up to my graph. And I'm going to draw a rectangle. There's one rectangle, so then at 3, I'm going to go up to my graph and sketch the second rectangle. On the right-hand side, right-hand sum, I'm going to start on the right and go up to my graph. And that's a very, very tiny rectangle. Oops, I missed. And then still from the right, and sketch my graph. So since we want to find area, you could count the boxes. That's fine. I'm going to estimate my y values. So for this one, we've got 3 as the width, and then all the way up to here, I don't know, that y value, these go by 2s. I think that's at 21. And then another width of 3, and this looks like it's, it's not quite 8. Let's go with 7.5. All right, take out your calculators. Let's add it up. This sum is 85.5. Okay, so now let's do the left. I've got a width of 3, and this rectangle has a height, I'm going to say a height of 3, and then 3, and this one has a height of, let's go with that 7.5 again, because it's the same y value at 3. So a left-hand sum, this is an overestimate. I've got all this extra area above the curve. And the right-hand sum is an underestimate because I'm missing all of these sections. This graph is decreasing, which makes the over versus under compared to the graph on the prior page was increasing. But if we draw these rectangles, we can see if it's going to be an overestimate or an under. A width of 3, these are horrible estimates. Ideally, we would have done at least a width of 1, what would have been a better estimate, but we're just following directions. It said 2 rectangles, so that's what we did. Oh, okay. Here's a little summary. You can pause the video to write this down. This is what I was just saying about decreasing. If the function is decreasing, then the right-hand sum, the rectangles that have the right corner on the graph, will be an underestimate. The left-hand sum, when the left of the rectangle is on the corner on the graph, is an overestimate. All right, so here's another one. Suppose the velocity of an object in meters per second is given by the velocity function t plus 8t minus t squared. Estimate the distance traveled during the first 5 seconds between 0 and 5 using n is 5. So let's find the width. So the end point is 5, the beginning point was 0, and we're dividing into 5 equal sections. So that's 1. What I made here is a table of the time values from 0 to 5 in our velocity function. We could do that ourselves. The prior problem, they didn't give us an equation. All we had was those graphs, which is why we estimated the y values. This time, we actually have a function, so I can calculate the y values. So there they are, same values, that's just smaller. Okay, so we're going to do a left-hand sum, a right-hand sum. And because it said use 5 rectangles, we're stuck with a width of 1. I can't do a better estimate at a half or a quarter. Here's our left-hand sum values to add up. a width of 1, type them in your calculator. Right-hand sum. Width of 1. Type them in your calculator. So the distance traveled is approximately between, well, no, the distance traveled is between 100 and 115 meters. I cannot get any more specific than that based on the directions. Just for fun, I'll draw you some rectangles. So if I go up here to the 5, that's my right-hand sum. Kind of hard to see on all these boxes there. Whoa. So you can see how it's an overestimate with these pieces over the curve for this right-hand sum. And this graph is mostly increasing. Just at the very end is it decrease. So the other way is F is increasing, then the right-hand sum is an overestimate. That's these. And the left-hand sum is an underestimate. For either an increasing or decreasing velocity function, the distance traveled is somewhere between those two estimates. And as we go on in this unit, we will get more specific on how we will get more exact values. Please use your calendar to see what the homework is and complete that before our next class.